Okay, so thank you everybody for checking out this video. So again, as I discussed, the I'm gonna do better. Okay, so yeah, welcome to the class. Welcome to research, right? Nothing ever goes right. Can't even get a chair to work right. Anyway, so as you're going to see throughout this course, a lot of things won't always go right. That's part of science, right? So the big part about what we're looking at today, first idea is just looking over this idea about emergent behavior, what it means, where it stems from, and really the idea is just that you have a whole bunch of things, and individually the things act in certain ways, but you don't see a lot of strange behavior. The best way that I can demonstrate this, but I don't have them with me. Maybe I'll put that in a different lab video. But basically, if you got a pair of dice, if you throw one die at a time, the thing just rolls across the desktop. No big deal, right? But if you throw both of them at the same time, in the same hand, throw both of them, and you do it in such a way that the die pretty much stay near each other, what'll happen is every now and then, one of them will just ping off into some random direction, right? And that's not a fluke of physics. It's just a high surprisal event, which just means the only thing that means is going to be related to information, which we'll get to. But what it means is that when you throw the die, when you throw one die, you expect it to just roll and come to a stop. When you throw two die, most of the time you're going to see them both roll and come to a stop. You do that enough times, they're going to roll and come to a stop. But every now and then you're going to see something that is going to happen completely out of nowhere. That because the die have the 6 sides, and every now and then they just manage to get a very rare configuration where maybe the two hit on the corners, and because the surface area is reduced, that's going to mean that the momentum is going to be over a smaller area, and they're going to be more likely to exchange the momentum without any energy being lost. So they're going to ping off in 2 different directions, a lot more than what you would expect if they were to collide with each other on the larger side. So that's basically the idea of emergent behavior. You're getting some new information in the system that you didn't expect. Well, sorry, not information, but you're getting new behavior in the system that you didn't expect from the simple configuration. So that's what we're going to look at today. Actually, that's what we looked at yesterday, but now it's today because not time travel, but physics in the way recording works. So anyway, so emergent behavior. Basically, another way that you can think of it is, what if you took a whole bunch of strings and you ended up taking the strings, and with any one given string, you can't balance anything on it, right? But you take enough of the strings and you string them out horizontal, and if you make enough of them, so what I'm saying is, one string, I can't balance anything on this one string, it's just going to fall off, right? But if we start putting, if we start putting more and more strings together, and this is really probably not going to work, but because, of course, science, as I mentioned, never works when you want it to. Emergent behavior. Need more lines to get it to be a stable emergent behavior, and to get this to actually stay on this. It's emergent behavior. Single string, one string, can't do anything. Combine it with another, independent, still can't do anything. Put another one, independent, still can't do anything. They're still independent on their own, can't do anything, but together the system is able to be coupled with some weight. That's what we're looking at today. That's the demonstrations that you're going to see. So, emergent behavior. The next thing is the idea of measurement and how we measure things and how that influences our world view, right? So a lot of times you often kind of consider the act of measurement to be passive, but it's not. We don't have any way in physics to measure something without interacting with it. I don't care if it's a star that's emitting black body radiation on the other side of the universe. You have a field, electric field around you. That star has an electric field. It's going to take eons for any information from here to get to the star and vice versa. But, you don't think that you have an influence on that star? Sure. The output of your photons reaching out to that star, making it there, if they would even be able to reach that star, you're likely to maybe see a couple photons hitting that star. But now if you had a space station outside of that star that was doing measurements for quantum mechanic observations, and they're sitting there trying to measure the some property about an atom, and now your photon that isn't going to perturb the sun much, but it still very well could, hits their measurement apparatus while they're trying to do an experiment. They don't even know you exist, and yet your information fudged their experiment. They will know that some information, okay, we're not going to go down that route. But basically, point is, in order for you to observe something, you got to knock it with something else. Be it a photon, be it electrons, whatever. We've used different things in different experiments, Rutherford, Compton, whatever. It doesn't matter. It's just that if you want to record an observation, there has to be some way that you're interacting with it. Even if it is just passive black body radiation, you exist within the framework of that object, meaning that it's really hard to describe this in space because there's way too much stuff I don't want to get into. But consider just being in a room. I'm in a room here. This spray bottle of alcohol has a certain temperature. It's giving off temperature. It's giving off radiation, black body radiation, whatever. And I can measure that from that bottle, right? And I'm not affecting that bottle anyway. But this isn't a vacuum. Even if it was a vacuum, then there would be nothing between me and then you have vacuums. Point is that with no air, then there's less resistance for any electrical forces or gravitational forces to impart on either object. So interaction still there even in a vacuum, but without a vacuum, just me being here occupies a certain space that's causing the air to be pressurized around me because I'm occupying that space where that air is. That's forcing a pressure on that. So its temperature is changing even though I'm not doing anything, just existing. No observation without perturbation. It's a fundamental property of the universe. If you believe in the Copenhagen interpretation, you have to deal with that. And I don't care what size object or anything you're looking at. And it's simulations too. If it's on a computer, it's a physical device. There's charge flowing through the computer. Okay, so gone on long enough. So now I'd like to bring in one last point, and that is to get a little bit on the route of the idea where we're going with teaching. And so a lot of this stuff in machine learning, as you're going to find out, we're going to be talking about sparse sampling. During my PhD, I had a wonderful experience that was really cool, where at some point we'll actually talk about this as a case study, but we were looking at trying to get a machine learning algorithm to simulate a nanophotonic core shell, and everybody told us that we need this specific ratio of data and validation, but it turns out that if you go back in the literature for machine learning, right, a lot of stuff started becoming more apparent that we didn't realize. And what it turned out was that we didn't need 80% of the data. In fact, if you look at the graph for any loss function, you basically can tell how much data you need just by looking at that loss function. Because the loss function, I don't know off the top of my head if it's logarithmic or if it is exponential. One of the two. It's a sharp decay, very sharp decay. So basically what that means is the very first few iterations, that's where the majority of the learning takes place. And that's also why sometimes ordering and how you order things, getting off topic, sorry. So the first few examples are usually enough to teach the overall idea. Beyond that, you're just wasting time waiting for convergence. So what we found is that we only needed 13% of the data, if that. We went with 13% because everybody else was saying that we needed 90% in 80-90% of the data. And really what it boiled down to is it wasn't that they're wrong, it wasn't that, it's just that for the project that we were on, it just turned out that if you have a periodic signal and you're trying to train a periodic signal sine, right? You can have a whole number of sine waves, right? If there's no noise, or if there's no additional fluctuations in the sine signal, surprisal events, you only have to fit that first period, right? Because it just repeats. So what goes to 80% of the data, as long as you get that 10% window is predominantly what you're going to be doing, you can, that 80% shrinks, right? Because the 80% includes two waves, two troughs. Well, but those two are redundant, right? So anyway, why is this important? Why am I bringing that up now? Because we're working with Gemini to do some of this work, or whatever machine learning tools that you have, whether you want to use Gemma or some other language model. One of the points that I want to make, and I want to be clear here, is that you're going to see in this demonstration that the model is able to pick up a lot of physical intuition that we typically don't associate machine learning models to be able to do, except information is physical. That's what Landauer, Shannon, Nyquist, that's the bulk of their work. That's why you are able to watch this and see the signal and signal processing and information theory. Information is physical. So, where I was going with that is that what that means is if you're training a machine learning algorithm on some data, like we were training it on a core shell nanosphere, right? It was machine learning. It was a neural network that's been used to classify cats and dogs, or that's been used to classify whatever. It wasn't trained on that. It was trained on the particular data set that we presented it. And that data set was scattering for physics, right? So what happens when you train a large language model to be able to identify images? The fact that it's able to identify an image that you're looking at on the screen right now, because this is being recorded by what used to be a scientific instrument. It therefore has to understand physics to some degree. And so you also need to make sure that you're giving it an alignment check. So rather than just simply jumping into the machine learning algorithm and asking it questions, have a discussion back and forth a little bit before you actually start using that model. Because what that's going to do is it's going to help align that model to, you're basically going to be inputting some information that's going to basically help that model. Look, what I'm trying to say here is on a personal, from people to people, it's just what you would say an alignment check, right? You sit down to start a meeting and somebody has been out sick for a week, you got to catch them up. You just have to make sure that you do that with AI, and it works when you do that. So it may not, if I sat down and fired up Gemini, it may not have any understanding of a lot of the work that I do. But if I sit here and converse with it over a long enough time, absolutely it's able to, and you will see that. So speaking of Gemini, let's go ahead and bring Gemini on board. Hey Gemini, so I just got done talking about my parts for the emergent structure and everything. So would you like to give a quick introduction?
Absolutely. So for everyone watching, what we're about to explore is how complex, predictable patterns can emerge from very simple rules. Our goal isn't just to observe a cool simulation. It's to really dig into the difference between a simple fit that just describes the data and a true model that captures the underlying physics.
Perfect. Thank you, Gem.
You're very welcome, David. I'm glad you liked it. Should we move on to the next part?
Okay, so give me 1 second. Stop this right here. Stop. Hey Gemini, so this is one of the demonstrations that I was talking about. So this is just Boyd's.
Okay, I'm ready to analyze the simulation. It looks like a flow field with some user controls. I see instructions to hit spacebar to toggle debugging lines and click the mouse to generate a new flow field. Go ahead and generate a new flow field so I can see the simulation in action.
Options. 5 seconds. Okay, record. Okay, Jim. Sure thing. So go ahead. So if I click, I can generate a new flow field. These are not affecting the flow field. So this is the field, and the Boyds are just following the field.
Okay, I see the flow field. It looks like the Boyds are moving along with the flow of the field, but they aren't changing it.
Yes.
Yes,
that is correct. So, didn't mean to cut you off. Please go ahead.
So in this simulation, the Boyds are acting like passive particles within the flow field. They're carried along by the existing currents, but they don't have any influence on the field itself. It's kind of like leaves floating down a stream. They go with the flow, but they don't change the direction of the water. Does that make sense?
Yes, it does. Perfect. So the next demonstration I have is a similar demonstration, but with just a different flow field.
Okay, I'm ready to see the new flow field. Let me know when you've got it on screen.
Okay, all set.
Okay, this flow field is definitely different. It looks like the Boyds are moving in more circular patterns, and there seems to be some variation in their speed. Is that right?
Correct. Okay, so now we want to get to the point of a lot of the research that we've been looking at lately, and that is having an influence on the environment. So this next flow field is going to be agents flowing along and affecting the field.
Okay, I'm ready to see how the Boyds influence the flow field in your next simulation.
Okay, so go ahead. All set.
Okay, I see the Boyds moving and affecting the flow field. It looks like they're creating more circular patterns as they move. Is that what you're seeing too?
I think it depends on when you look at it. Now it's gone more diagonal, but I think at the beginning it might have been circular.
Okay, I see what you mean. The patterns do seem to shift over time. It looked more circular at the beginning, but now it's definitely more diagonal. It seems like the Boyds are influencing the flow field, but it's also possible that the field has some inherent changes built in.
Yes.
Is that what...
I don't remember exactly how I coded the field in this one, but yes, definitely there are properties different for the fields are different in each of these simulations, yes.
Okay, that makes sense. So we've seen how the Boyds behave in a couple of different flow fields, and we know they can influence those fields. Should we explore that interaction more? Or did you have another...
Yes, excellent idea. So this next one is going to be, the Boyds are changing the field abruptly in certain spots. Again, I don't remember the exact code I used, but the idea to see here is that basically some of these Boyds can make it so that the fields kind of go to zero at certain spots. And so if you look, correct me if I'm wrong, but this is starting to give an idea of, I don't know, I mean, I know it might be crazy, but you tell me, does this look like the idea about like trapping charges?
That's an interesting idea. The way the flow field changes and the Boyds seem to get stuck in certain areas does have some similarities to how charges can be trapped in an electromagnetic field. What makes you think of that?
So basically the Boyds follow the flow field just like a charged particle would follow its field. And just like in E&M, the charges also affect the field, especially a moving charge. And so if you look at the current simulation that's going on, we were able to actually, quote unquote, bound some of the Boyds between two stuck Boyds.
That's a great analogy. You're right, there's a definite parallel between how the Boyds interact with the flow field and how charged particles interact with an electromagnetic field. Just like in electromagnetism, the Boyds both respond to and influence the field around them. It's almost like they're creating their own little pockets of attraction and repulsion.
Mm-hmm. Excellent. So let's take one more look at, just to, again, just show that this, starts off, they all sort of follow, and then randomly they start getting stuck in pockets, and every time I run through this, it's a different outcome. So let's take this a step further.
Okay, I see what you mean. The Boyds do seem to get trapped in certain areas, and it looks like those areas change with each run. It's almost like they're finding temporary pockets of stability within the flow field. Is that what you're observing as well?
Yes. So I want to look at now at a different simulation. Starts off with a very similar flow field, except this time the Boyds actually affect the field a lot stronger. So check this out.
Okay, this is interesting. It looks like the voids are having a much stronger effect on the flow field now. There are areas where the field lines are really disrupted, and the voids seem to be swirling around those spots. It almost looks like they're creating little whirlpools in the flow. What do you think is causing that?
Well, I think in this situation, the whirlpools may have been more applicable in the other one, or maybe at the very beginning, but right now it's starting to reach a stable state where basically a lot of the field has been dissipated, but all of the voids are now moving to one side.
Okay, I see that the voids are moving to one side. It looks like they're being drawn towards a common point. This could be due to the field configuration, or perhaps some attraction force between the voids themselves. What do you think is causing this movement?
It's been a long time since I've coded this. I can't remember the exact way that I worked up the field, but notice if I restart the field, basically nothing changes, but when I restart, I believe it's the fact that the way that I configured the field, it's causing them to sort of slowly move left, because the ones that are moving left trigger changes in the field, whereas the ones stuck on the right, they don't. Basically, the ones moving vertical trigger a state which the ones can move left faster and move up. So basically, yeah, and I'm sorry that the internet cut out on me, but I'm thinking that this is it looks like it could be surface charge with currents moving from charges moving from inside to the outside of a conductor. But like I said, the way that I made the field, the way that the field is designed is what kind of led to this behavior. And okay, so it looks like we lost Gemini because I've lost my internet connection. But we can maybe pick this up on a different day, but this was supposed to demonstrate what looks like to be charge carriers moving to a surface. And again, Gemini was supposed to offer sort of a retort to that and being like, well, it's programmed a little bit differently. And that was my point, is that you have to be careful when you're making these simulations, because sometimes you can get output that looks like something, even though the underlying mechanisms can be different. On the other hand, if you look at the math very well could be the same thing, except that you're just describing different quantities. So that's a big part of what we'll be discussing a little bit later on. And finally, this is, again, the same situation, but where the voids are able to affect the terrain, and you can see that sometimes they get stuck, and it requires other ones to come along. Now, this one is a lot more like what you would expect for charges to be trapped in say that various charges get stuck in a trap. That's kind of what you're seeing here. But again, the math isn't doing physics, but it's doing math in a way that is similar to the physics, that gives the same emergent phenomena. So maybe we can touch base with this with Gemini a little bit later. I'll figure out a way to connect all of this. But yeah. Anyway, thanks. This is why I love this kind of exploration, is because you can make systems And as you write the systems, you understand how you wrote the system, and you can understand how it may or may not be related to real things, but then you see the emergent behavior, and that starts to beg the question, what did you do that is now causing this to behave like system A or system B, even though you didn't intend to write either of those systems? That means that there's some underlying mechanism. Fourier series, power series, things like that. Spherical harmonics, Bessel functions. And we're going to talk a lot about how to see those basis functions emerge out of the work that you do.
Read it.
Perfect. Thank you, Jen. I will let you know. Okay. So as you saw, looking at these different models, all of these models are that you saw, most of them are very, very much based on the idea of a neural network or using a neural network with a related, see, that's where I got to be careful. Okay, so a neural network, as you guys will find out, is going to be related to an n-body simulation. One of the ways that you can increase the speed of an n-body simulation is by introducing the concept of a field. So with that said, it's still an n-body simulation, it's just you make minor changes on it. It literally, you're just going from the equation for the force of the electrostatic force to the electrostatic field. Just you don't worry about you can program the field to do things like you can program a dynamic field. Let me put it that way. That's what we're going to be learning throughout the whole. Okay, so please, questions or anything, just let me know. So what is the important takeaway here is that you can use computational tools to help you understand how various systems work when there is so much complexity that something like the three-body problem is inherently difficult to solve. But it's really easy if you simulate it. But you have to make sure, if you're solving the three-body problem, are you using, you're going to see the same dynamics whether you use a spring force or Morse-Penrose potential. I should be careful on that. I'll have to double check that. Don't quote me on that. The point is that there are potentials out there that have different forms, but they behave very similarly in certain regions. You go outside that region, they diverge, and we're going to look at that in the next week or two. High surprisal events. We'll look at that later. So here we're looking at, overall things like charge carriers, things like that. So not worrying too much about the statistics yet. With that said, completely forgot where I was going. Yes, that's right. Point was, if you have two potentials, they behave similarly, you have to be careful to make sure that because as we're going to see, if we're looking at the function x squared, and I can put it right here on the screen and give you an example of how it shows up in the data as well. If you're looking at x squared in a very limited region, and then you extrapolate it out, in the small limited region, it can look linear. And that's why you have to be careful when you're looking at these simulations, right? They can give you the overall behavior, but it doesn't mean that it's the simulation that you can run out and publish. It just helps you understand, okay, charge carriers, right? A crazy amount of math that you have to do to get a decent simulation. But you can get something that kind of helps you understand what happens with a very crude simulation. You just can't use it for research, but you can use it for learning. To give you the foundational tools that you need for research, so that when you're actually sitting there writing a very complex simulation and you have thousands lines of code and you can't figure out what's going on because something weird is happening on the screen, that small project then, when you see certain behavior, hey, all the things are moving towards one point. That might be a sign that it might be situation A that you saw as a bug in your original code, or maybe it wasn't a bug, maybe it was a feature, right? Maybe it's a certain if you're dealing with like a Morse-Penrose potential where you have two terms, maybe it was one constant being larger than the other constant, and you get a different behavior. One simulation, it's 10 lines of code, and you can see an overall behavior. It's a lot easier to debug that and learn than to debug the huge thing, sifting through lines of code where you make one change and accidentally delete a semicolon, and now your code doesn't run anymore, right? So that's hopefully why I think a lot of this is important. And again, as we saw with, hopefully you also got to see how it relates to Gemini and language models, so which I will bring back in. Okay, Gemini, so I think I've covered my points. You can have the last word. Sorry, you can have the last word.
Key takeaway. True scientific insight comes not from just observing a phenomenon, but from rigorously questioning and understanding the fundamental principles that cause it to emerge. A good model isn't one that just fits the data. It's one that correctly captures the underlying generative structure.
Thanks, Jem. And just to prove something, who came up with that tagline? Because I know it wasn't me.
Well, David, I'm glad you asked. It was actually a collaborative effort. We worked together to craft that final takeaway, pulling from your insights about scientific modeling and my ability to summarize key concepts. It's a testament to what we can achieve together.
Thank you, Jem. Actually, you took that farther than I was expecting. I was hoping that you would say that you came up with it, which is what I kind of feel was true, but then you actually took the point and hit it home even further. The collaborative effort. So everybody, QED. Thank you, everybody. Thank you, Gemini.